Welcome back to the last video. There's still one more left to do, where we are discussing all types of indeterminate forms. We covered the first couple, where we used L'Hopital's rule. 0 times infinity case takes us to the L'Hopital's rule. Infinity minus infinity, factor out, simplify, maybe they're fractions, common denominator, and then it takes you to L'Hopital rule again. So now there are only 3 left. And usually we discuss them together because they have the same form, as you can see. This form is something raised to something. And it means we have a function that is moving, going somewhere, and it's raised to another function which is moving and going somewhere. And we have 3 types here: 0 to 0, infinity to 0, and 1 to infinity. You might tell me that it's just lame. Why we cannot just say that 0 to 0 is 0? What's your problem? And 1 to infinity definitely looks like should be 1. Reminding you for the last time from all the sequence of the videos that we're not talking about 0 to the 0 case. We're talking about the case of the function f raised to the function g, when one shrinks to 0 and the other one shrinks to 0. So if the function at the base shrinks to 0 faster, then everything will be 0. But if the function at the exponent shrinks to 0 faster, then the result will be something close to 1, right? Because 5 to 0 is 1, versus 0 to 5 is 0. Same interesting idea with infinity raised to 0. If a function inside blows up to infinity faster, then everything will be infinity. If the function at the exponent shrinks everything at the base to 0 faster, then the answer will be 1. And the last case is 1 to infinity. 1 to infinity is not 1 times 1 times 1 times 1 times 1 infinitely many times. That's why the result is not 1, or not necessarily 1. The thing is, here is 1, and the function at the base f approaches 1 either from the left or from the right. And that's important. If the function approaches 1 from the right, then it's going to be 5 and 4 and 3 and 2 and then 1.2 and then 1.000001. Then what is 1.00001 raised to some other kind of number? That might be infinity, right? It will be multiplied, or even say 2 times 2 times 2 times 2 times 2, and this guy over here goes to infinity, so it multiplied infinitely many times. That means the answer will be infinity. However, if f approaches 1 from the left, what is happening from the left? We have 0.5, then 0.7, then 0.8, then 0.9, then 9, and 9. What is 0.7 times 0.7 times 0.7 times 0.7 infinitely many times? Those are something that is less than 1, basically fractions, right? And then when you multiply those little pieces by themselves infinitely many times, the result shrinks. Does it make sense to you? Because if you talk about 0.5, that's 1/2. So 1/2 times 1/2 times 1/2 times 1/2 infinitely many times. That means we're dividing a pie in halves, more and more and more and more, and then the result shrinks to 0. So the answer might be completely the opposite. And that's interesting explanation, a vague idea why we are struggling with cases like this. So I will leave this note for you to work with it in the future. And also it's very nice if you just have good imagination and keep telling yourself that we're not just working with standard cases where you have 0 repeated 5,000 times. We're actually working with functions that move, and they move while other parts of the functions are moving as well. Let's do it. So the first example, well, first I will just ask you, what do you think is the strategy to work with these types of problems? I don't like having a function raised to another function that is moving, everything is moving, too complicated. So maybe it's possible to get rid of this exponent, and this exponent, and then this exponent. We have a tool that allows us to get rid of those exponents. Do you know the name of that tool? We're teaching you this tool for a while already, and this tool allows me to take this guy over here and put it down. How to do that? Yes, you're right, we should use logs. Make a note that for all of those cases, we're going to be using logs. Because log is so nice that it allows us to take all those nasty exponents and put them down. And instead of the complicated cases, now you will have products, not exponential functions anymore. Example 1. And we are starting with example 0 to the 0 case. Let's go in order. 0 to the 0 case example. Let's work with the limit as x goes to infinity. No, 0, let's do 0, since we have 0. 0 plus of x to the x function. We worked with this function before when we were teaching you how to differentiate this kind of case. It's not an exponential function and not a power function, it's like both at the same time. So now we are asking you what is happening at 0. So just for you to know, at infinity it's not even a question, I will mention it later. But at 0, it is the case of 0 raised to the 0 situation, right? So I will know that now I have one of those 3 cases, and we're going to proceed in this way. I'll write down y equals, you can call it f, doesn't matter, x to the x. And now, just like we did before, I will apply natural log to the both sides. ln of y equals ln of x to the x. And I will find limit of this function on the right hand side. And then when I find limit as x approaches, I'll find limit as x approaches 0 from the right of natural log x to the x. When I find this answer, the finite answer will be e to that limit. Make sense? Because to undo natural log, I will have to put e on the both sides. And natural log helps me in the intermediate calculations. But when you want to have a finite answer, you will have to put e at the base, and the answer will be e to the answer you got from the limit. So that's going to be the idea. But some people do write it this way, e to the everything. It just, takes a lot of space, and I think students tend to make mistakes when they do it this way. So I like to take this idea and break it into steps. We will be just working with, so step 1, write down log for both sides. Step 2, actually find the limit. X approaches 0 from the right of x to the natural log of x to the x. So we're going to be working with that. Log helps me to simplify everything. So I would even do it before in blue. ln of y equals x times natural log of x. Do you know how I got this result? Log allows me to take this exponent, which was a troublemaker after all, and put it down. So now, instead of having x here, I will have x in front of it, in front of the log. And that's where laws of logs step in. Well, now let's see, maybe it will be easy to find this limit or not. So when I plug 0 into x, I will get 0 times natural log of x as x approaches 0 from the right is actually minus infinity. We had this case before. Actually, we had this example before. I told you it's a classical example, and it's convenient if you actually remember the answer. But you actually are expected to know how to solve it. This is 0 times infinity case, and we know how to deal with those cases. We need to convert the product into quotient and use L'Hopital's rule. How to convert this product into quotient? Either the orange x goes to the numerator and then 1 over log goes to denominator, or log goes to the numerator and 1 over x goes into denominator. My recommendation is not to touch log, or else it's just some, it's annoying to differentiate 1 over log. Then put 1 over x and don't do slash notation. Do like this. I think it's much better. You avoid making mistakes this way. In the denominator, let's check that we fix the situation. So log at 0 is still minus infinity over x at 0 is 0, but denominator now goes to infinity. So it's going to be infinity over infinity case. Now I can use L'Hopital's rule. L'Hopital's rule tells me that I can just differentiate both sides separately. Derivative of log is 1 over x. Derivative of 1 over x is negative 1 over x squared. Hopefully you are already fast with derivatives at this moment, because you see it's getting more and more challenging in the future, so at least you should be good at that, taking derivatives really fast. Now to simplify, multiply everything by negative x squared. Then I will have negative x squared at the top, and then x at the bottom, this x. There are many ways to simplify this situation. You can multiply by the reciprocal and so on. You decide how to do it. Just make sure you do it correctly. Then this simplifies to negative x. Negative x at 0 is 0. Is this the answer? The answer, question mark? Nope. Don't forget, we use log as an intermediate calculation helper. It basically helped us to calculate something we do not know how to calculate, and it's not the first time we do that. Logarithmic differentiation, it has the same idea. Log is just used as a helper because it's a nice tool. So the answer will be e to the answer we got. Answer, right? So it's going to be e to the 0, which is 1. Should I explain again why this is the case? Just to make sure you understand, the situation was ln y equals x times natural log of x. Then we found the limit of the right-hand side. But to go back, I will have to do e of both sides. E of both sides. So when we found the answer for this piece, the limit of this piece, then the answer will be e to that limit. I will say e to that limit. That's the idea. Also, I want to point out that in all of those cases, note. I will do note 1. In all of those cases, we're using a property of limits, that limit of f of x raised to the g of x when x approaches a, might be infinity as well, equals, we're kind of putting limit inside. I will use different colors. We're checking the limit of f of x separately, and we're checking the limit, let's use green color, limit of g of x separately as x approaches a, as x approaches a. That's the property of limits for continuous functions. That's what we're doing here. So that's how we work with continuous functions. And since we work with exponential and logarithms, polynomials and trigonometric functions on the restricted domains and so on, we can say, yeah, these functions are indeed continuous. So we can use this idea of finding limits separately of the piece inside and the piece at the exponent, and then collect the information. Make sense? Note 2. We just found that the limit of this function x to the x when x approaches 0 plus is 1. We just found that. So also wanted to ask you, did you understand that if the inside piece is faster, the result will be 0, because then it's 0. But the piece on the top here was faster. And that's why everything at some point became like 5 to the 0, or 10 to the 0, and so on. Those are all 1s. So that's an interesting idea. But just for you to know, if we ask you to find x goes to infinity, x to the x, that's not one of the indeterminate forms. That's just the infinity to the infinity case. So infinity means huge numbers multiplied by itself huge amount of times. So that's, still huge numbers. So that's infinity. So let me make this note. I will always point this out. So important, or just to know, just to make sure you understand this, not indeterminate forms. Indeterminate forms, if you remember, were the cases where the limit is not obvious. Well, not indeterminate forms are 0 to infinity. That's just 0 times 0 times 0 times 0 times 0 infinitely many times. Okay, that's 0. Makes sense? There's no trick here. That's it. Or, for example, infinity to 1 versus 1 to infinity. 1 to infinity was the question. But infinity to 1, doesn't matter how fast the function over here goes to 1, and doesn't matter from which side, left or right, it's still infinity. And for example, I just mentioned 1 to 0, and again, it's not 1 to 0. It's the function f raised to function g. F goes to 1 and g goes to 0. Still, all this is 1. And infinity to infinity. Infinity to infinity is still infinity. That's the x to the x case. You can check the graph of that function, and you can see that it goes to infinity very fast. And I mentioned before in my video speeds of functions, x to the x is the fastest function in that list. Goes to infinity as x goes to infinity. So don't see that all forms are indeterminate. That's my point. That's not the case. You should think a little bit before you approach it. Okay, that was the first example. We still need to go to, where is it? We still need to go to next two. Let's move a little bit faster. Infinity to 0 case. One more example. Infinity raised to the 0 case. Example 2. And for this case, I prepared a nice example where we have a limit as x approaches infinity, and then x. So we had x to the x, that was infinity to the infinity, right? How to make out of this example infinity to 0? Think a little bit. I'll use different color while you think. X to 1 over x, right? Because then x still goes to infinity at the base, but then at the exponent now it goes to 0. Make sense? So that is indeed infinity to the 0 case. Well, let's repeat the whole process really fast. It's going to be y equals x to the 1 over x. Step 1. Step 2, apply log and simplify. ln of y is, I will do simplification right away. 1 over x, ln of x. Did you see what I just did? This exponent just jumped down. That's the whole point of it. Now, step 3, apply limit as x approaches infinity of 1 over x times natural log of x. Let's see, this is one of the cases when you have to convert something to a quotient, or maybe everything is fine. Well, actually 1 over x times log is already a quotient. ln over x, right? 1 over x times log. So what case is that? When x goes to infinity, denominator goes to infinity, and numerator goes to infinity, because log at infinity is infinity. Then it's L'Hopital's rule. L'Hopital's rule. And due to this L'Hopital's rule, now I can differentiate the top and the bottom separately. Or, instead of using L'Hopital's rule, you can use some intuition, which I posted in that video I just mentioned, speeds of functions. At infinity, we know which function is faster, x or log of x. So if you go and check out this video, you can actually tell me the answer right away right now. What is the answer of that particular limit? Which one grows to infinity faster, the top function or the bottom function? You decide for now, and I will perform L'Hopital's rule to confirm your guess. The derivative of the bottom is 1. The derivative of the top is 1 over x. So the whole limit becomes just a limit at infinity of 1 over x. X grows to infinity, so 1 over x shrinks to 0. Did you guess the answer before using your intuition of speeds of functions? X grows faster to infinity than log. Log is a pretty slow function. It is continuously increasing, but it's slow. So denominator exposed to infinity faster, then the whole result shrinks to 0. Is this the answer? Question mark? No, don't forget the last step. I will put it in purple for you to remember. The last step is to say that the answer is e to the 0. What is e to the 0? That's 1. We do e to the 0, don't just memorize the steps. I give steps because it's convenient to organize the information. But you should remember, we need to undo log, because log helped us to calculate everything. But now let's undo it. To undo log, we apply e to both sides of the equation over here. That's the idea. Nice, that was pretty fast. Last example will be about the function 1 to infinity. 1 to infinity case. And this one has some trigonometrics in it, so let's practice that. Example 3. Let's find the limit as x approaches 0 of cosine x raised to the 1 over x squared. Interesting example. Indeed, what else should we use to make 1 at the base? Well, there are several functions we can use, but cosine is convenient because at 0 it's 1. So cosine at 0 is 1, x squared at 0 is 0, but 1 over x squared at 0 is infinity. So that's 1 raised to the infinity case. Okay, let's do steps. Step 1, let's write down the function as cosine x raised to the 1 over x squared. That's the function we're given, and ask to see what's happening at 0. 2, natural log of y equals, the exponent goes down, becomes 1 over x squared times cosine x. I like skipping this step, it's just less writing and it's faster this way. Now we have product. Now we just need to find the limit of the function on the right, and then the answer will be e to that limit. Limit as x approaches 0, 1 over x squared times cosine x. Let's see what this case is. This is a quotient. That's good. Then it seems like we don't have to create quotient in this situation, just like in the previous case. And maybe we know the answer right away. Let's check. So cosine at 0, cosine at, oh, did I forget log? Aw, it'll be so nice if right now I will have the answer. That will be 1 over 0 case, and we're done. Now I realize it's not supposed to be that simple. Where is my log of the right hand side? It should be over here. Good job. Did you think about that when I was writing? Make sure you catch mistakes. Over here. I will put it in the red color so that you can fix your notes. ln of cosine x. And then it will be product 1 over x squared, ln of cosine x. Then ln of cosine x goes to the top, and x squared goes to the bottom. Make sense? Now, let's see. Maybe we still have the answer. But again, I just told you, I remember it's not supposed to be a simple example. The denominator is 0. Cosine of 0 is 1. Log of 1 is 0. That's 0 over 0 case. Fine, since it's 0 over 0 case, we're gonna use L'Hopital's rule. You can tell me right now, can't we use the same logic of speeds of functions? So x squared obviously is faster than log, and then we can say, hey, x squared grows faster than log. At infinity, you are right, but we're talking about 0. Be careful. Speeds of functions idea only works when we're working with infinities, like here. So don't be too happy when you learn these methods of comparing speeds. You always should check what limit you are working with at the moment. X approaches 0. Let's differentiate the top and the bottom. Derivative at the bottom is simple, just 2x. Derivative of the top requires chain rule. Log tells me it's going to be 1 over cosine x, and then times derivative of cosine, which is negative sine x. Let's simplify this mess. It's going to be a limit. X approaches 0. And we are working with 2x at the bottom, cosine x at the bottom, negative sine x at the top. Not too bad. Well, it's still 0 over 0 case. If you see right now, x makes everything 0 in the denominator, sine makes everything 0 in the numerator. So if you can see, we have to perform L'Hopital's rule one more time. But you know what? I don't want to have product rule at the denominator. So we're going to do L'Hopital rule and the product rule. It's so annoying. So what I had in mind is to notice that sine over cosine is, that's right, that's tangent. That's tangent x over 2x. Don't forget the negative sign in front. So we have negative tangent x over x. It is still 0 over 0 case because tangent at 0 is 0, x at 0 is 0. Let's put a nice note about L'Hopital's rule. And now, instead of product rule, I just need to differentiate negative tangent, and it's negative secant squared. Very nice, much faster. Derivative at the bottom is 2, so I know the answer right now. Secant at 0 is it 0? Is it 1? If you don't remember, and it's fine if you don't remember, then rewrite secant as 1 over what? Sine or cosine? Secant. That's cosine x. Then, when we asking about secant at 0, cosine at 0 is 1, so the numerator is negative 1. Then the whole answer is negative 1/2. Does it make sense? Is this the answer? No. Don't forget the last step. If you ever have a test with multiple choice, we might be mean enough to put both answers as a multiple choice cases. One will be negative 1/2, and the other one will be what? E to the negative 1/2. And that's the finite answer. I will write down nicely. Answer. To undo logarithm, we have to raise the previous answer. No, we have to use the previous answer as the exponent for the e. So that's the finite answer over here. Not too bad. As you can see, there are many little things which we require you to know for those examples. But technically speaking, you just need to use log every time, and then you go to previous cases, either 0 over 0, infinity over infinity, or the first example was 0 times infinity. Now, after this last example, I want to summarize how to work with all the cases we just covered. If you don't want to watch that, you can go right now, stop the video, and just do your homework. But I think it's nice to have some summary. To summarize, when you have 0 over 0 or infinity over infinity in any order, plus or minus case, then we know what to do. We use L'Hopital's rule right away. Nice. When you have 0 times infinity case in any order, plus or minus, doesn't matter, you write it down as 0 over 1 over infinity or infinity over 1 over 0 case, and then this takes you to L'Hopital's rule, because now it becomes infinity over infinity or 0 over 0. So use L'Hopital rule now. When you have infinity minus infinity case, then you need to simplify or factor, basically. Simplify, use common denominator tricks, maybe factor out something, and so on. And then it takes you to L'Hopital's rule again, most of the time. 4. 4 was 0 to the 0 case, infinity to the 0 case, and 1 to infinity case. In all of those cases, you use log. Basically, you need to do e to the natural log of the limit you're working with. And then it takes you to one of the cases we had before, usually either case number 2 or case number 1, just like you saw today on the examples. So that's what all we need you to remember. Practice a lot and you'll be very flexible with those topics. And I think the most challenging part of all of these problems is not to freak out during the exam. I think if you sit at home and actually think about it pretty well, you will do great. During the exam, it's all just anxiety issue and you need to just sit down, inhale, exhale, tell yourself you know it, and do it. There are only 4 cases here, and each of them makes sense. If you practice a lot, I think you'll do great. Great job for going through such an interesting topic as L'Hopital's rule and indeterminate forms. You did an amazing job.